Okay, so, and the first types of proofs that we're going to be going through fully starting on Monday are algebraic proofs, where it's just kind of going through the steps of solving an equation and then you're listing the reasons why each step works out. So for example, like these first four, actually these first five are used quite a bit in algebraic proofs. And when you learned how to solve equations, you probably heard of these properties, but we don't really like write them next to each step when we solve equations. So the addition property of equality is the property that says as long as you add the same number to both sides of an equation, the equation still remains true. So say you have an equation 4x minus 3 equals 5. Your first step to solving for x would be to add 3 to both sides to get the x alone. I'm going to write it this way though. So I'd have 4x minus 3 plus 3 equals 5 plus 3. So adding, that may not be how you write it. You probably would just write it underneath plus 3, but adding the same number or quantity, because you can also use addition property of equality with segments or angles. So adding the same number, quantity, value to both sides of an equation keeps the equation true. That's the addition property of equality. All right, so then the next three, same idea. Subtraction property of equality, subtracting the same number or quantity from both sides keeps it equal. So if you had this equation, 7x plus 6 is equal to 20, your first step would be to subtract 6 from both sides. So 7x plus 6 minus 6 equals 20 minus 6. So subtracting the same number, subtracting the same measurement, that could be a measure of a segment, measure of an angle, from both sides keeps the equation true. Division property of equality, dividing the same number from both sides keeps it true. So if you have 5x equals 15, and then this, I'm just going to write the way you normally would write it. You would divide both sides by 5. That would be the division property of equality. And then the last one, multiplication property of equality, multiplying the same number to both sides of an equation. So if you had something like this, I'll do, if you had 1/2 x equals 4, because I could divide both sides by 1/2, or to get rid of a fraction, you could multiply both sides by the reciprocal. So I could multiply both sides by 2 to cancel out that 1/2. That would be the multiplication property of equality. Okay, so those you've definitely used before, probably heard of the properties, but we'll be actually using them in proofs starting Monday. Distributive property, you've used a lot, you've heard of. I know you know what that is. So there's kind of two separate definitions here, one of which is maybe, it's something that can be combined with the distributive property, but you might not think of it as the distributive property. So I'm going to kind of separate these. So one definition is multiplying a single term and 2 or more terms inside a set of parentheses. And then a second definition is the adding together 2 terms with a variable. So combining like terms essentially, and I'll show you why that's grouped in with the distributive property. So for example, A, what you would normally see as a distributive property. So if you see something like 3 times the quantity x plus 2, you know that you would distribute the 3, and you would get 3 times x plus 3 times 2 is 6. Okay, that's normally what you think of as the distributive property. Then what B is saying is if I have like terms, so let's say I have 4x plus 5x, and I can combine those to 9x. Okay, that definition is saying that's also distributive. But here's why. If I know you did this in algebra with factoring. Factoring is well, factoring is the reverse of multiplying, so I could use the reverse distributive property. Since both of these terms have an x in common, I could think of this as the quantity 4 plus 5 and then times x. Okay, so if you thought of distributing the x, you would get 4x plus 5x. But I'm kind of working with that in reverse. So the 4 plus 5 gives me the 9, and then I have the x. So that's why it's kind of grouped in with that distributive property. So if you see that you're combining like terms in a problem, that would fall under the distributive property. And then substitution, this is also something you use a lot. So if you have something like this, so say x is equal to 7, and then we have this expression, 3x minus 2. So substitution is saying if two things are equal, so if x is equal to y, x can be substituted in for y in any equation, y could be substituted in for x in any equation. So if I know that I have the expression 3x minus 2 and x is 7, I can substitute the 7 in for the x to get 3 times 7 minus 2. Okay, so anytime you see that you have an equation or an expression and something is being replaced by something else, that's substitution. All right. Just want to make sure I'm not flipping the page. Are we good if I flip this? Okay. Then we get into property of opposites. This is also, you can write property of opposites, but this is also the inverse of addition. Could somebody give me, bless you, could somebody give me two numbers that would be considered opposites? Like, what does opposites mean? -1 and 1. So two numbers, one's positive, one's negative, but they would add together to be 0. They cancel each other out. So adding a number to its opposite to create a 0. So just in general, say you have a number a. So a plus its opposite, which I'm going to put in parentheses just because I'm putting plus a negative. A plus its opposite is going to be 0. So then a specific example, if we use 1 and -1, so 1 plus -1, we know equals 0. So if you see that you're adding two opposites together to get 0, then you are adding, just in general, you're using addition, but you're using the property of opposites or the inverse of addition. Then we have identity of addition. So this says the sum of any number and 0 is the original number, so I can add 0 to anything, and I'm not changing the identity of the number. So I have, say, a number, any number a plus 0 is going to equal the number I started with, a. So any number a plus 0 is a. So like 3 plus 0 is still 3. The way I remember identity again is you're not changing, like the identity of the 3 doesn't change. When I add 0 to it, the 3 stays the 3. The identity stays the same. So then identity of multiplication, same idea. You want to start with a number, multiply it by something to get the same number. So any number multiplied by 1 is that original number. So I can multiply any number times 1, and it doesn't change the identity of the number I started with. So specific example, 3 times 1 is still 3. And then we throw in there just definition of subtraction. So just what it means to subtract, because that will be used in some of our proofs. So the taking away of a number from another number, or adding the opposite would also be true. So if you see kind of in simplifying that you're doing something just like 9 minus 4. Or if you see it written as 9 plus negative 4. So yes, you're seeing addition, but one number is positive, one is negative. They're not opposites because they're not adding to 0, but you're adding the opposite of 4 to the 9. So if you see that in a problem, that would just be the definition of subtraction. Okay, then we're going to get into some other properties of equality. The next 3 are properties of equality. So reflexive property, this is going to come up quite a bit in certain types of proofs, which says basically anything is equal to itself. So for every real number x, x is equal to x, so a number is always equal to itself. And that could be any expression, any segment, any angle is equal to itself. So you might see, like I'll just put a number, like 5 is equal to 5. It could be a whole expression, so x plus 3 is equal to x plus 3. Or as we're going to see, I'll even throw like a segment and an angle in there. So you might see like the measure of AB is equal to itself, or the measure of angle A is equal to the measure of angle A. And you'll see why when we get to proofs, why you would even need to say that, because obviously something is equal to itself, but you'll see why that's necessary to say. Symmetric property is something you probably use a lot when you're solving equations and don't think about it. So this is saying that I can switch the two sides of an equation and the equation is still true. So if x is equal to y, I can just flip it around to say y is equal to x. So how many of you, when you solve an equation, if you were to get this as your answer, 4 is equal to x, how many of you, before you circle your answer, would switch it to say x equals 4? I know I do that. That's the symmetric property that says, I mean, you don't even think twice about it, you just do it, you know it's true, but that's the symmetric property. So if I know 4 is equal to x, then I can switch it around to say x equals 4. So that's the property you're using when you do that. Or that's the property that says you can do that and it's still true. All right, moving along. Did I go too fast? Are we good? Oops. Okay, are we good? Okay. Transitive property. This one just comes up a lot. I feel like it comes up a lot too in like standardized questions. This is where you have 3 numbers or quantities. So it says if A is equal to B and B is equal to C, then A is equal to C. So notice if you have A and C are both equal to B, then they must be equal to each other. If they're equal to the same thing, they must be equal to each other. So I'm going to try to put like a geometry example of how you would see this. So I could say if AB is equal to 3 and CD is equal to 3. So if I see, okay, both of those measures of those segments are equal to 3, then I know AB must equal CD. They must equal each other. So it's written kind of differently because I didn't write AB equal to 3 and then 3 equal to CD. But if you see that 2 quantities are equal to the same thing, they must be equal to each other. So we'll see that quite a bit. Now getting into more geometric properties, postulates, theorems. And some of these we've already talked about, or we've at least talked about definitions. So we've talked about midpoints. Midpoint theorem says that if point M is the midpoint of segment AB, that means that segment AM must be congruent to segment MB. So I'm going to just draw a sketch here. So if I have segment AB, and then M is the midpoint, so that means segment AM is congruent to segment MB. So that's just what it means to be the midpoint. So how this would be used in a proof, for example, is you might be given this information, M is the midpoint of segment AB. You can then make this conclusion, and the reason why you're making that conclusion is by the midpoint theorem. So that's kind of how we'll be using these. Definition of bisect. So bisect, for whatever reason, this definition throws people off. I'm not sure. Yes, it divides something into two, but it divides it into two congruent parts. So that's the key there. It divides it into two pieces that are congruent. So that could be, we use this with both segments and angles. So again, if, let's see here. Say I have segment, I'll draw a segment and an angle example. Segment AB, and then see I have this line, I'll call it line little m. And I know that this bisects it. If I'm told that that line bisects segment AB, my conclusion then is these are the same. I should probably put a point here. I'll put point C here. So then I know that segment AC would be congruent to segment BC. Okay, so if I was told line M was bisecting segment AB, my conclusion is segment AC is congruent to segment BC. And that could also be true with angles. See, I have an angle here. And then I know that this ray bisects it. I'll just put bisects. I should label my angles here. I'll call this angle 1 and then angle 2. So if I know that that ray, or I'm told that ray is bisecting the whole angle, then I can say angle 1 must be congruent to angle 2. Okay, so just understanding bisect not only divides it into two, so that bi, think like bicycle, that would mean two, but it's two congruent pieces. That's the key there. And then we have the supplement theorem, and this later on when we get into definition of supplementary, there's a key piece with the supplement theorem why they're different. I know I don't have them written right next to each other, but supplement theorem, the key, it says if two angles form a linear pair. This is the key for the supplement theorem. The two angles have to form a linear pair. Then the conclusion is they are supplementary angles. So first of all, what does it mean for two angles to be a linear pair? Because we talked about that in chapter 1. Anyone remember what a linear pair is? Two angles make a line. Yes, linear, they make a line. So if I have, this is what the picture would look like for a linear pair, something like this. So say this is angle 1 and angle 2. So they share the same vertex and they form a line. What does it mean to be supplementary? Yep, they add to 180. And we had talked about how the angle of a straight line is 180 degrees. So that should all make sense, hopefully. But the key for supplement theorem is the two angles that add to 180 have to form a linear pair. They can't just be two random angles that add to 180. So the conclusion then is the measure of angle 1 plus the measure of angle 2 should equal 180 degrees. So this is what it means to be the linear pair. This then is the conclusion. They're supplementary, they would add to 180 degrees. Okay, definition of congruent segments. So this is just what it means to be congruent. We've talked about this definition. So if two segments are congruent, then their measures are equal. So if you want to make this note, this notation is telling you that the segments are congruent. I'm just going to put segments congruent. The conclusion is their measures are equal. So segments congruent and then measures equal. That's the difference in the notation. So when you don't put a segment or don't put a line above the AB, you're talking about the measure, how long it is. And the measures, you use an equal sign. The segments, you use a congruent symbol. So let me kind of draw an example here. So here we have segment AB, segment CD, and then I know segment AB, I'm just going to put like a 3 here. I know that's 3. So if I'm told, say I'm given segment AB is congruent to segment CD, so then I just labeled, okay, I know these are congruent, so therefore I know the measure of AB should equal the measure of CD, and the measure of AB is 3, so CD must also be 3. That's kind of how I can come to a conclusion. But that's notation as well, just making sure you understand when to use the congruent symbol versus just an equal sign, and then what the bar above and not above means. Definition of congruent angles, same idea. If two angles are congruent, then the measures of the angles are the same. So again, when you have the M in front, this again is measures are equal, or measures equal. I'll just draw kind of a similar, I'll draw two angles. Say this is angle A, this is angle B. And I know angle A is 20 degrees. So if I'm given angle A is congruent to angle B, then I can make the conclusion, okay, the measure of angle A must equal the measure of angle B, and I know the measure of angle A is 20 degrees, so therefore the measure of angle B must be 20. All right, we're almost through. Just bear with me. Am I okay to switch this? Okay. Definition of perpendicular lines. So perpendicular, two lines that meet at a right angle of 90 degrees. So if you have two lines, and the key is you can't ever assume something is 90. So you have to see that right angle symbol or be told that an angle is 90. But if you see that, you could say those two lines are perpendicular. Or if you're told two lines are perpendicular, you can make a conclusion like, okay, this angle is 90, depending on what your proof is looking for. Definition of a right angle is an angle that measures 90 degrees. So if you're told something is a right angle, you can conclude that it equals 90 by definition of a right angle. So if I know, or I'm given this picture, and this is angle A, and I have the right angle symbol there, my conclusion is the measure of angle A is equal to 90 degrees. by the definition of a right angle. Then we have the definition of complementary, two angles whose sum is 90. So complementary is adding to 90. So I'll just draw one picture here. Here, Bryce, let me give you a pass. Okay, two angles whose sum is 90. So say I have this picture here. I have this other ray coming out, and this is angle 1, this is angle 2. So not necessarily a bisector, but based on that picture, since I know angle 1 and angle 2 are combined going to equal 90 degrees, I know they're complementary. So the measure of angle 1 plus the measure of angle 2 would equal 90 degrees. So they would be complementary. Definition of supplementary, similar idea, but again, this is different from the supplement theorem. So supplement theorem on the previous page is the two angles have to form a linear pair. Here they do not, so I'm going to draw this one differently. Let's just say that I have, here's one angle A, and I know that's 100 degrees, and then I have another angle B, that's 80. So notice I did not draw them as a linear pair. They are not forming a line, but because they add to 180 degrees, they're still supplementary. So I know the measure of angle A plus the measure of angle B is equal to 180. Okay, but they're not a linear pair. If they were linear, if you're told something's a linear pair, that's the supplement theorem. Then the next two, segment addition, angle addition. So very similar, it's just obviously one segments, one's angles. So you can, well, I'm not going to read through this. I'm just going to draw it. So we have used this already in chapter 1. You had to use this in some problems. So let's say I have this segment. So I have segment AC, B is somewhere in between A and C. And so then I can say the length, and that's what this is saying here, the length of segment AB plus the length of segment BC should equal the length of the whole segment. Okay, so again, this is AB plus BC should equal AC, is what this equation is saying here. We've used that before in chapter 1. Hopefully visually that makes sense. The two segments added together would equal the entire segment. So angle addition is the same idea. But I have to label this here, so I need another angle in there. So let's say this is A, this vertex is B, this is C, and I have a point D. So what I can see is, so my entire angle ABC is composed of two different angles. If I added these two angles together, I would get the entire angle. So I could say the measure of this angle, which is ABD, the measure of angle ABD, plus the measure of this angle here, which is DBC, angle DBC, should equal the measure of the whole angle ABC. Okay, so I can add those two angles to get the entire angle. Yes, almost done. 2 more. And then, yeah, you'll have some time to get started. I'll show you what to do for the practice for today. So notice there are multiple right angle theorems. So they're all kind of grouped under right angle theorem. But this right angle theorem and given what you know about right angles, hopefully what these say makes sense. So it says perpendicular lines intersect to form 4 right angles. So one thing I want to point out is if you know that you have 2 lines that are perpendicular and say only one right angle is drawn in, if you know they're perpendicular, you know these other 3 angles are also right angles. So you know all 4 of those angles are 90 degrees. So that's what that first one is saying. All right angles are congruent. That should make sense because they're all 90 degrees. Perpendicular lines form congruent adjacent angles. So what does adjacent mean again? Next to. So perpendicular lines, any 2 angles that are next to each other, they're all 90. So they're all going to be congruent. If 2 angles are congruent and supplementary, then each is a right angle. So hopefully that makes sense. If they're congruent, they have to be the same measure, and if they're supplementary, they have to add to 180. The only way for that to be true is if they're both 90. And then if 2 congruent angles form a linear pair, then they are right. So that should hopefully make sense too, given what we know about a linear pair. It's kind of these 2 together, because they would have to form a line in order to be congruent and form a line, they have to be 90. Okay, so that's all kind of grouped under right angle theorem is what you could say for any of those, but those are all grouped under there. And the last one, vertical angles theorem, says if 2 angles are vertical angles, so if you know they're vertical angles, you know they are congruent. All vertical angles are congruent. So as a reminder, vertical angles are formed by intersecting lines. So like here, this is angle 1, this is angle 2, those angles are vertical angles. Angle 1 is congruent to angle 2. But you also have another pair of vertical angles. These are also vertical. So if I call these 3 and 4, angle 3 is congruent to angle 4. So if you're told angle 1 and angle 2 are vertical angles, your conclusion is, okay, they're congruent. I know they're the same measure by the vertical angles theorem.